Okay, so I was asked about the practical, just from a student that can't attend. You can survive the course without attending the practicals, but you'll need for that friends that attend, and you get information from them as well. So the practicals are unstructured. Today and this week, so the practical we have today, and the same copy of it that we have Friday, so just go to one, is you using Julia. You're using Julia, and I'll just kind of get out of there, and you can use a bit of Julia. Otherwise, it'll be with the tutors, and they're very knowledgeable, and they can help you with homework questions and also things that you don't understand. Okay, the tutor sometimes takes it in a certain direction, but there's not really structure. So yeah, you can survive without attending the practicals. You can also, as recording here at home, hopefully survive without attending the lectures. You maybe survive without doing the course. Okay, any questions? More? All right, so let's go to another example, and this one has to do with something called Markov model. So a Markov chain is a random process, and it often gives a nice little linear algebra example. We won't do that per se in the course, but it's one of the units here. So if you look at topic 5 in your project, so one of the topics is about Markov modeling. And some of you might have heard about reinforcement learning, so Q learning, etc. So Markov chains have to do with that in quote artificial intelligence. So this is a story. So think of, here's a very simple example. So think of the weather. This is from the Statistics with Julia book. That's in the Statistics. So here is a very dumb model for the weather, but it still captures something. So every day we can have a different type of day. We can have a fine day, cloudy day, a rainy day, cloudy day, a rainy day, a fine day, etc., etc. So weather alternates between these days. Okay? Now, a Markov chain means that if today the weather is fine, then with probability 0.5, it will become fine again, and with probability 0.4 it will be cloudy, and with probability 0.1 it would be rain. So what is the sum of the weights on the out edges of every node? The sum of the weights of the out edges of every node? 1, right? Because certainly next day it will be either fine, cloudy, or rain, right? So you can describe the out edges like that and see, right? Rain 0.2 plus 0.5 plus 0.3, that's 1. Okay? So this is a model, and it can go quite far because this model captures dependencies. So the next day's weather depends on the previous day's weather. The Markovian property means that if we know today's weather, then what happened in the past doesn't matter. Okay. And a lot of dynamic machine AI methods are kind of related to this, especially in the realm of reinforcement learning. Who's heard of reinforcement learning? At least heard the word? Reinforcement learning? Okay. And who so what's the greatest achievement of artificial intelligence of the decade? Perhaps the most publicized one? Everybody now speaks about AI. Even people that don't know what a function is speak about AI. What was the kind of a landmark thing that AI did a few years back? Yeah. Right. Yep. So the Go thing. Right. So Go, the game of Go. Some of you perhaps who plays Go? Anybody? Go. Some. Okay. All right. Yeah. Okay. So Go is a harder game than chess in a sense. It requires a bit more intelligence, so we believe. And then, computers were able to beat Go. The underlying mechanisms for that are reinforcement learning, and for that you also need to understand Markov chains. So there's this underlying structure is there as well. But this is a very basic Markov chain. Now, when you see data like this in a graph, you can immediately think about a matrix. Think about a matrix. So take the matrix P, square matrix P, where Pij, the ijth entry, is the probability that the state in the next time instance is going to be j, given that at the current time instance it's I. This is conditional probability. It means if the state is currently in state I, okay, where I and j are in the set 1, 2, 3. Okay, so we map each of these states to 1, 2, and 3. For example, 1, 2, 3. Okay, 1, 2, 3. And then we say, okay, these are conditional probabilities given that at time t, we're going to then, time will move by 1 day to time t plus 1. What is the chance of going from state I to state j? So the matrix P have those entries Pij. Now, you told me that the sum of the edges is the sum of the weights of the edges going out from each node is 1. So what is the matrix P times the vector 1, 1, 1? So the matrix P acting on a vector is going to give us another vector. What do we have here? What is multiplying a matrix by a column vector of 1 is due to the matrix? Or what is it result in? Yeah, go ahead. The sum of rows. The sum of each row, right. So the sum of each row. So now if you look at the ith row, the ith row is you are now in state, for example, fine. You're in state 1. Okay? This is I equals 1. You can get to j equaling 1. You can get to j equaling 2. Or you can get to j equaling 3. So what are the sum of the elements of each row? What's the sum of the elements of each row? You can either go here or there and there. It's a probability. 1. Often if somebody asks in probability force what's the sum of something, it's going to be 1, because that's all that can happen. Okay? So this matrix has this property. And Pij's are non-negative. Okay, because they're probabilities. This is what we call sometimes a stochastic matrix. And here it is. Here it is. Here's this matrix. Okay. Here's this matrix. So you see, you go 0.5. That's from fine. You get to 0.4. 0.2. So this matrix, for example, this 0.1 here is going from fine to range. It's the probability of going from state 1 to state 3. So this is one way to input a matrix in Julia, just like in MATLAB. But so far we have a Markov chain. Now there's a whole bunch of things we might want to do with this Markov chain. A whole bunch of things we might want to do. One specific question that already comes about is, hey, if we now run over a long time horizon, we're going to transition between fine, cloudy, cloudy, fine, rain, fine, cloudy, etc. Weather's going to change. What's the long-term proportion that it will be raining? How many days will it be raining? From 100 days or from 1,000 days? Yeah. Well, okay, so that's a great answer. That's an uninformed answer. If we don't know anything else, we say, well, there's a chance here and here and here, and it's a third. But actually, look, it kind of depends, because if this is cloudy, you've got 50% chance of it being cloudy, whereas from fine, you only got 10%. So there's not so many entrances to rain. So maybe rain is not as possible. It's not as possible, right? I mean, if you would change this to epsilon to be a small number, and change this to epsilon to be a small number, and change this to epsilon. So if it's rainy, like in the desert, right? If it's rainy, the next day it's rainy is highly unlikely, and the chance of becoming rain is unlikely. It'll be much less than that. That's a question we might want to ask. So what we have in this code snippet is answering these questions in a variety of ways. Now, the mathematics here, there's actually quite a lot of math for each of these ways, but I'm going to explain mechanistically what each of them does in terms of the matrix P. Okay? And they all give us the same answer. So a lot of what's in this statistics modulia book is kind of getting the same answer in various ways. A lot of the things that you might want to consider doing in your demonstrations, your 2 or 3 demonstrations in the topic, is kind of getting the same thing from different ways. I mean, in a sense, mathematical property is, hey, I can get this in several different ways, and you want to show that different ways converge, okay, or agree. So that is what we're computing here. But let's look at each of the ways, and let's see in terms of the linear algebra and the Julia what they mean, without fully understanding exactly why they hold, because we're not doing, of course, a normal chain proof. So the first way says that if you multiply the matrix P by the matrix P by the matrix P, and you do that many times, or first let's say k times, then this is actually, we can show using probability that the ijth entry of this matrix is actually the probability of getting to state t plus k. This is plus k, that k is bj, given that xt. Okay, so this here, our data is kind of the one-step transition probability, going from day t to day t plus 1. This is for k equals 1. It's actually beautiful that by just using a bit of conditional probability, which we don't have to know about if you don't know conditional probability, but you can work this out. And this is part of the probability course in a sense. That you go from state I to state j in k steps, it will be the i's j's entry of the matrix p times p times p times p times p k times. That's kind of very small. You take the matrix, and we can just write this. We'll write p to the power k. So when we write a matrix power, we had some confusion of this with this in the quizzes last semester in MATH7502. So when we write a matrix power, we mean the matrix times itself. It's not the element-wise power. Okay. Now, if this is true, how about this? Why don't we just take p to a very, very high power? So let p run for a very, very high power. And then, well, intuitively, where we started doesn't really affect where we are. And then we'll read the probabilities of those rows. So let me just run this snippet here. So I'll take this matrix P. So that's a matrix P. Now I'll do P to the power 100. Or let's just do P squared first, and this might not work on this one. Okay, because we might need to use linear algebra, maybe for that. This is the packet linear algebra. You see, the resulting matrix P2 here, notice that it's also a stochastic matrix. So sum of the rows is 1. The sum of the rows is 1. Well, if we just want to verify that, then let's just call this P2. call the matrix, that's the name of it. And then let's do P2 times 1's 3. Okay. Again, when you multiply a matrix times 1's, you sum each row. Okay. And you get 1, 1, 1. Okay, so it's also a matrix sums of 1. Let me put this as a comment. So here's a matrix P2. Again, semicolon suppresses the output. Without semicolon, we see the last expression in the cell. That's a matrix P2. Okay. So let's look at the matrix P3. Or let's not call it anymore P2. I'll delete this. And just P to the third power, which is equivalent to doing P times P times P. Okay? It's the same. I'll just do P to the third. And times here is matrix multiplication, is not element wise. Okay. That's P to the third power. Now, notice how the rows are starting to be kind of close. They're starting to be close. Now, the reason is that after 3 days, P to the third power says, so the IJS entry, for example, let's look at this one. This says, after 3 days, if in the first day I was in state 3, what is my chance of being in state 2? So the chance of being in state 2 after 3 days doesn't depend so much on where we were initially. Look, here it depended 0.3, 0.2, 0.4. Here the chances are much closer. Okay, let's take 4 days. They get closer. So let's take 100 days. And at least up to 4 decimal points, but way more, we see that the probabilities are the same. And each row sums up to 1. So each row is a probability distribution. So if we now want to know what's the probability, the long-term probability of being rain, what's the long-term probability of rain? Or what's the long-term proportion of rain? Yeah, 25%. Say again? 25%. It happens that in a smoke of chain it's 25%. This 25% is in no way immediately obvious from the problem data. It's in no way obvious from the problem data. Of course, if you're measuring a situation, you can just measure the long-term probability of being rainy. But this is actually a model of transitioning between one weather state to a different weather state. So real weather models don't use 3 states, they use thousands of states and also use memory back a few more states. Okay, so that is one way. So we can, of course, from that, let's take from this the one colon entry. And what this gives us is the probability distribution from the first row, but we could have taken that one, could have been any row. So this is a probability distribution not of just being rainy, but being fine, cloudy, and rainy after many, many times. Okay, so this was all well and good. The reason we show this, we speak about it without matrices, but you also see matrix multiplication in Julia. But now let's do it in a completely different way. Okay. So again, these ways, the actual theory of why this holds, well, you need to use computation probability, and the theory for the other things, you need a bit more Markov chains. It's not really part of this course. So let's go to the second. This was a way, and it's also this way has some problems because we had to compute p to the high power, so we had to do a lot of matrix multiplications, and we didn't know exactly what power to take, so we took 100 and we treated that as infinity, right? So it's certainly not the best one. So here's a different way. Different way claims. So pi I has nothing to do with 3.14. So in Markov chains, pi is like the stationary probability. Pi I is limit t to infinity of the probability of xt equaling 9. Okay. So that's your long-term probability of being in state I. We just computed pi 1, pi 2, pi 3. Okay. So that pi, that pi 1, pi 2, pi 3, this thing was one way of computing pi. This is pi we're looking for. So here's a claim. This is pi I. Claim this. Let pi I be this. Then pi 1 times pi 2 times pi 3 times the matrix P equals pi 1, pi 2, So sum pi I 1 to 3 equals. Okay, so we have a column vector times a matrix P, sorry, row vector times a matrix P equals a row vector. Okay. And this claim follows from the fact that pi is a stationary distribution. Again, this is not take it as a given. It's a property that these properties are going to adhere to, and they also need to be a probability. Now, first of all, can we represent this? Can somebody represent this condition in terms of in vector notation? So let's just denote pi. The vector pi is a vector of pi 1, pi 2, pi 3. Okay, of the row vector. So how can we write this? Let's do an inner product of pi with something. Inner product of pi with what equals what? So why don't we write pi times the vector of 1, 1, 1. What does this need to equal? 1, right? So we could have just written this as the inner product of pi and 1 equals 1, and this is a vector of 1. Okay? Inner products are free reading for next week, and if you did last semester, then you did a bit of inner product. So or we can also write this if we would like. Yeah, we can just write this. So effectively, now we have a system of how many equations are here? 3 equations, right? And this is one more equation. So we have 4 equations, 3 unknowns. Okay. Now there's actually a unique, if this Markov chain is nice, and by nice we mean that we don't get stuck in a given state and never go out. There's actually going to be a unique solution. And from the theory of linear algebra, we're going to learn, well, we need 3 equations and 3 unknowns. We don't need 4 equations. And it turns out that this P, we can actually, from these, we can throw arbitrarily one of the equations. We can throw away one of the equations. So let's first of all, let's try and transform this into the typical system of equations that we know how to solve, and we're going to do a lot of in this course, or at least some. AX equals B. Okay? You've seen this perhaps before in linear algebra. Right? In linear algebra, AX equals B. And if you had kind of a course that really made you go to the physiotherapist afterwards, you did a lot of row operations on H, and then you got X. Okay? All right. So let's transform that into AX equals B. Why? Because we can solve AX equals B. One of the basic things we want from mathematical software that does linear algebra is to solve AX equals B. Let's just see if we can solve AX equals B. So let's just take some arbitrary A. Look, I'll do A ran 3 by 3. This is some A. Okay. This is some arbitrary A. Let's take B. B ran 3. Okay. I can also do this. I can do A comma B. That's a tuple A comma B, so we see them both. But we don't see it so nicely, so we see the A in kind of not matrix. Okay, but that is our A. This thing is A. See A semicolon, semicolon, and A, and this is. So if we want to solve AX equals B, how do you do it in MATLAB? Do you remember? Matrix, but just with one character. A divided by B. Okay, so I mean, if you again divide by B, so it's kind of like thinking, or sorry, B divided by A. Okay, so like that. Sorry, B divided by A. So see, this is the solution. This is going to be the vector such that A times X equals B. And now this backslash holds a lot in. So who's seen this backslash in MATLAB? Okay, so this solves the whole system of equations. Sometimes it does more. Maybe there are a system of equations that's overdetermined and it finds a least square solution. It does more. So if this is X, let's now do A times X. And let's, oh, sorry. So, okay, so now we have some. Okay, let me just fix this. So I'll do B as a rand of 3 by 1. Just so you see. So let's take B not as just a list, but B is really a matrix, which is a vector of 3 by 1. And now we don't need this. Wait, what am I doing wrong? Oh, sorry, it's not B divided by A, it's A divided by 2. Okay, sorry. This XA slash B is the solution. Yeah, it's not going to it because I want like to bring the A there. But that's a famous backslash, and we'll use it. So now look, if I do AX, I want this thing to be B, and to see that this thing is B, let's just do AX minus B. And if we get a 0, well, yeah, we got a 0 up to numerical error. Okay, this is a 0. So often in numerical linear algebra, things are not exactly 0, but they're certainly, this is close enough to 0. Like if you want to do, what you can do is you can do the maximum. You can do the absolute value of this. Now look, I'm going to do absolute value, and it's going to get angry because it'll say, hey, I do not know. So Julia says, I do not know how to do absolute value for an array. So absolute value is a scalar function. But what you do a lot in Julia is you put a dot here, which broadcasts absolute value to each of the elements of X. So this is now the absolute value. Okay, and you can do the maximum of this, which is of course going to be this. So this is a maximal error, right? So this snippet has quite a lot in it. It took some arbitrary matrix A, it took some arbitrary matrix B. By the way, we assume there is a solution, but when you take random matrices, the A would probability 1 not be singular. Okay, there's always an A. It might be a condition, but it won't be singular. We found X, and we actually verified that AX minus B, so this was vector subtraction, right? So it's element-wise vector subtraction. We found that the maximal error is very low. So effectively 0. Let's do it for 300 or for 3,000. Let's do 300. The same goes. So that was a 300 by 300 matrix, and we solved it. Okay, back to our problem. Questions? So we're now here. We're now here. Now, here we want to convert this system of equations to be of this form. To be of AX equals B. Why? Because we know in Julia how to solve AX equals B. Okay, we can, by the way, we can write about that just so we see. So I'm going to do escape A cell above. I'm going to do escape M to make this a markdown cell, but I could have just gone to cell type markdown. I'm going to write, this is like a heading. This is example in your system. And then I'm going to do in LaTeX AX equals B. And it kind of describes what I have. Okay. Finding the solution. Okay. So the solution is X, let's do it inline, X equals A inverse times B. Okay, so the second one, the solution is X A inverse. Yeah, you saw how I did the inverse, that was in line. By the way, we didn't use an inverse here, so mathematically we do inverse, but what Julia did is use row operations, which is in no way computing the inverse and multiplying it by B. But if we just want to see that, sorry, let's go again to a 10 by 10, or to a 3 by 3. Okay. And next cell will actually say what B is. And let's also get inverse of A, that's the inverse matrix of A. Okay, this is inv of A, that's the inverse matrix of A, times B. Sorry, I didn't want B, I wanted X. What X is. This is the solution. Okay. And this is the solution via an explicit inverse. And you see that you get the same thing. But the first way was much more efficient. In the second way, we actually computed the inverse, and nobody does this mathematically or in implementation. You don't actually compute an inverse. For a 3 by 3 matrix, if we do it for a 1,000 by 1,000 matrix, the numerical error that we have here would be much bigger, and this would take much faster. I lost you in this little game of inverses and numerical algebra. It's just an application of. So we've seen inverses, we've seen how to multiply things, we've seen transposes. And now for this application, we want to put stuff, and finally back to this, we want to put stuff in the form of AX equals B. Well, it turns out that what we can do is we can merge. I want to do this massaging. We can take the system of equations, we can do a transpose on both sides here. So let me actually write it like this. I'll write this was pi p equals pi. Now pi, most vectors we treat typically as column vectors, but pi is actually by default a row vector. So let's do a transpose on both sides. What's a transpose of pi p? What's a transpose of pi p? What's D, the matrix D times F if you transpose that? What's that? This is a small basic things that are MATH7501 stuff, but only this in terms of matrices. By the way, next lecture is going to be much slower, right? And step-by-step understandable. Here we're going all directions. But yes, Lee, what's that? Well, it's F transpose, D transpose. Okay? Right, so transpose actually flips the thing, okay? And you can just do that by matrix operations. You can see that this is okay, so if we now take transpose of this is going to be P transpose times pi transpose equals pi transpose. Okay, so I transpose both sides. By this dash, I mean transpose. Okay, transpose both sides. And if I do that, and what I can also do, I can now multiply pi by matrix I. What's matrix I? The identity matrix, right? So then I can do P transpose minus I times pi transpose equals 0, 0, 0. I could have just written a 0. Okay, so I do minus I and I pull out the pi transpose to the right. This is looking a bit like AX equals B, right? Looking a bit like AX equals B. It's looking a bit like x equals b, but we forgot this last equation. Then I want to stick this last equation here in terms of instead of the third row. So look at this thing on your right hand side. Okay. So you see, that's P. The top two rows are P transpose minus I. How do you see their P transpose? You see this is not P12, this is P21. It's a transpose. Minus I. The third row, we said C, I wouldn't want to be here, we replaced it, and we put this here. This is the third row. So this is a system of equations. Now we want to solve this system of equations. And this is what this code does. This is what this bit of code does. So, second way. This is what it does. It does P transpose minus I. It takes the first two rows, and then it adds a ones to the third row. Okay, that's the first two rows. Then the third row, and VCAT actually concatenates, sticks together. Your B, your right hand side, is going to be this 0, 0, 1. And this is now the real engine, A backslash B. So if we do this, again, you're not learning this in just if anybody's here in the first lecture and you see too many things, this is an expository lecture, so you kind of see what's happening in the course. Okay, so by the end of the course, you speak this language and you do these things. Don't stress if this is too many details. I stress a bit. Okay. So here, if we run this code, these are the probabilities which we get. 0.43, 0.31, and our infamous 0.25, the same ones. Questions about that? So the first way had no systems of equations, just took matrix powers. Second way actually solved the systems of equations, and we had to kind of sweat in preparing the systems of equations. System of equations are kind of everywhere. The third way has to do with eigenvalues and eigenvectors, and I won't speak about that because I'll move on to other things. But the fourth way is completely different. It's completely different. So let's actually see what's happening in the fourth way. The fourth way doesn't use linear algebra. The fourth way is your straightforward engineering thinking way of thinking, how long will I be in range? So if I present this problem to you, about 20, 25 minutes ago, you thought of it, and somebody said, well, range would be a third, then you thought a bit more, you thought, well, it's not going to be a third because the thing depends on the probabilities, and you think more and you think, well, how long am I going to be in range? You'll say, well, let's just try it. What do I mean by try it? Well, let's live life and just count how many days are range. But we're going to live inside the computer. We're going to simulate. We're going to simulate. So how are we going to simulate? Well, let's start. We're born. Let's be optimistic. We're born fine. Okay. And then let's use randomness, pseudo-randomness. So we do a lot of random numbers. We already did it for creating the matrices. Pseudo-randomness to either go here, here, or here for the next step. And do this again and again and again and again and again. Run this for 1,000,000 times. See what proportion of this 1,000,000 times we are in range. And it's very nice that we actually get the same number that we get from rather complicated mathematics. Okay, so we see that these things, well, there's some sense in this. So here's how we do this. I'll just annotate it. So to get line numbers, I did escape and L. Okay, that's useful for communicating. Let's do it. All right, number and state. So we start with zeros. So we're just going to count. We're going to tally how many were in each state. And our state is 1, and 10 to the 6 is going to be the number of simulation runs that we're going to run. This is how you do a for loop in Julia. Okay? For t in the range 1 to n. Okay. So what does line 26 do? What does line 26 do? Jelly? Right. Okay. So arrays are indexed in Julia like they are in MATLAB, not like they are in Python. In Python, the first element is 0. In Julia, the first element is 1. Okay. So number in state, the state element, add 1, because we just started. So we just started. What's the first iteration? What num state is going to go from a 0? It's going to become 1, 0, 0. Now here's a killer line. Here's a killer line. That global command, ignore that. That's because this whole thing is written in global namespace. So and for loops have their own scope. In Jupyter Notebook, you'll actually run without this. If you run Julia in the REPL, so by the way, Julia, you can run it also in the REPL. Who's run the REPL already? REPL? REPL. A digression for a second. REPL. REPL. So when you install Julia, and you just have basic Julia, this is a REPL. This is a Julia, it's kind of like the Julia command line. Look, let's give it 1 + 1, it's faster. Okay? Very good. So when you run it in the REPL, that you might need is global, otherwise no. It's just a minor detail, not so important. Now this sample, let's see if we can make sense of this sample function. So what do we need to do when we're finished with fine? We need to go to the next state. So now we need to choose probabilities. We're going to get a value either 1, that's the range 1 to 3. So 1 colon 3 is the range 1 to 3. With certain weights. The weights are going to be based on, and this is a kind of the important thing, how would you describe this from a linear algebra perspective? What is this thing that I'm highlighting? State is either 1, 2, or 3. What is it? It's the row with index state and all elements there. So it's the row with index state. So these are exactly the probabilities, because our probability transition matrix, the entries of it are exactly these probabilities. So it's either you're going to sample with these probabilities, or sample with these probabilities, or sample with these probabilities. You can implement some, and that's using Monte Carlo. So the phrase Monte Carlo, if you haven't heard, Monte Carlo. Has anybody been to Monte Carlo? Really? You've been to Monte Carlo? Did you make money there? Okay. The Monte Carlo, I think, near Italy and France, kind of on the border. It's like a little country, right? Yeah, so Monte Carlo, the phrase Monte Carlo, we call that creating simulations where the computer is tossing random numbers. The computer is not actually using real randomness, it's using pseudo-randomness. Okay, so it's using kind of a deterministic. Okay. So when we go here, this new state is random. But it's random according to these laws. And then what do we do here in line 29? We take this total number of counts. So, it counted how many days we were in fine, how many were in cloudy, how many. And we normalize it by n. We're dividing the vector by the scalar. Dividing the vector by the scalar. Let's see this one. So I'm going to do escape and B, and that puts a cell below. It says weights not defined. So weights is not defined because I need this thing called stat space. So the function sample and the function weights are from stat space. Oh, I hope it's this package. Okay. So we got to get our numbers. Now, you see, this is slightly off because this involves randomness, right? This is a Monte Carlo estimate. It's a Monte Carlo estimate of the 0 point. Questions about this? All right, 9:50. Oh, very bad. Okay, so we have 1 more hour, but we meet in 2 hours, and we're going to do digit classification of least squares. So see you then. It's in a different. That class is on the other side of campus.